Yes, sir.
Yes, sir.
Yes, sir. Yes.
Okay.
Yes, sir. Yes, sir.
Okay. Okay, so last class we are looking at Powell's method of quadratic fit. So you have to find 3 points here and fit the quadratic up. Okay, so that so for that we are using this handwritten equation. Okay, handwritten equation is being used. Okay, so you have to find A0, A1, A2, and you can fit a curve. And we looked at a example where we start with these 3 points. Okay, x1, y1, x2, y2, x3, y3. Okay. Okay, and we finally get this curve. There's some delay is there in the screen. It is coming very slowly. The internet may be slow here today. Okay, so now you can see that this Powell method is a one-shot method. You can fit it only once. And suppose you want to iteratively improve the fit. Okay, so for that, there is a moving quadratic interpolation by Powell. Okay, moving quadratic interpolation. Okay, so I don't know, this thing is very slow for this. What is the reason? I don't know. Okay, so this is illustrated with an example. So in the previous example, we started with 1.5 and 2. Okay, and we got the best point 1.3584. So this is one iteration. So how to continue these iterations? The one method is that now you reject this point 2 and you take this new point and the other 2 points on either side. That is this 0.1 and 1.5 on either side. Okay, and then you fit a curve through these 3 points. That is the new x1, x2, and x3. You fit a curve through them, and then you get the new point. So this red point is the new point. So then again round it. Okay. So this way you can iteratively improve the quadratic fit. So you take the best point and the point around it, and you get a new fit. So this is just the explanation for what I already said. Okay, so now the new x1 1.5. Okay, so you fit the curve. Okay, and then the best point we get is 1.38. Then the next iteration involves 1.38 and the 2 points around it. So this is 1.38 and this is the other 2 points. This is, I think the cursor is getting delayed. Okay, so you can repeatedly do this. So let me exit and reload. Okay, the cursor is taking a long time.
Okay, sir. Here also same issue, sir.
See, when I draw a line with the cursor, it is taking 5 seconds to go on screen. So let me check what is the. Maybe I have used this Vodafone instead. Are you able to see now?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Okay, so there's some internet problems here. Yeah, the IIT Wi-Fi only problem. Okay, so this is how the so this is how the Powell's iterative method works.
Sir, we can hear you.
Yeah, connection is gone. I think so. Okay. I mean, internet connection was gone. That is right. Okay. It has come back. It is okay now or?
Yeah, it's okay.
Yes, sir. Yes, sir.
Okay. So Powell's quadratic interpolation method is just like this only. So you take the center point and the two best points on either side. Okay. And you keep on repeating the iterations. So how to terminate iterations? The iterations can continue until specified number of iterations are finished. So sometimes you say you want 1000 iterations. So then it will do 1000 iterations and stop. Then, or we can specify a tolerance limit for the convergence of the objective function. So current value of objective function minus previous value divided by current value. It should be less than a certain value, and only then it will stop. And another thing is that the slope of f of x can be checked to be 0. Okay. So as your point comes closer and closer, the slope will be equal to 0. So you can give a tolerance for the slope, like 0.0001. And once that slope is reached, you can stop the iterations. Okay. The next method is called Newton-Raphson method. It is gradient-based method because it depends on first and second derivatives. So basically, it uses Taylor series approximation, which is truncated up to second derivative. So second derivative is there, third derivative and higher derivatives are taken as 0. So this exactly matches the definition of quadratic function. If you take any quadratic function, it will not have third derivative or more than that. So if you use Taylor series approximation, it will exactly work for quadratic function. But more than that, it will be an approximation. So what you have to do in Taylor in this Newton-Raphson method. So the user has to give a starting point x1. So this is starting point x1. The formula searches for the minima in a small range delta x from the starting point. This is the small range delta x from the starting point. And then it reaches x2. Okay. Then from x2 you repeat the search for another small range delta x and you reach x3. So what is the formula for finding x2 from x1? So this is the equation. x2 is equal to the previous point x1 minus first derivative at x1 divided by second derivative of x1. So by this Taylor series truncation, you can find the approximate location of the point where slope equal to 0. And you have to simultaneously check the slope value. So here the slope is approximately equal to 0. So then you can stop the iterations. So this Newton-Raphson method only checks the slope. Okay, so you can either reach minima or maximum. So Newton-Raphson formula is given like this. So x2 is the next point, x1 is the current point, then this is first derivative of the objective function at x1. This is second derivative of objective function at x1. So how do you find this first derivative and second derivative? So if you are human being, you can manually do the differentiation, but computers have to use this central difference theorem to find the approximate estimate of first derivative or second derivative. The first derivative is found by this approximate expression. So first of all, you have to find the value of delta x. This delta x must be a small fraction of the range, say 10% of the range. So if the range is say 1 to 10, then you can take delta x equal to 1 or less than like 0.5, 0.2, etc. Then you substitute all these things, you get first derivative, and you substitute all these things and you get the second derivative, and this has to be substituted here. Okay. And you get next point x2. Hence find x2. Now you have to check slope of x2, slope of the curve at x2. So if this the slope is approximately 0, or if it is satisfying within a given tolerance, then you can stop. But suppose x2 is here, okay, slope is not 0, then you need to further continue the search and find x3. So x3 is found from x2 from this same formula, okay, the same iterative formula. So we look at some example. Find the minima of the subjective function in the range of 0 to 6, and the exact value of optima is given for your reference. So the starting point we take as 1 because x is from 0 to 6. Okay, I take as 1. Actually, in the exam, you will be told which starting value to take. Only then everybody will get the same answer. Okay, and take delta x is 0.1. So that is less than 10% of the range. Range is 6. Okay, so then you find first derivative at x1. So you can use this central difference equation. So you will get -2. Then you find second derivative at x1. You substitute all these things and you get 36. So next point x2 is first point x1 minus first derivative of x1 divided by second derivative of x1. So it is 1.33. So you have started from 1, and next you have reached 1.33. So you have to check the slope at x equal to 1.33. The slope is coming to minus 3.73 and it is not equal to 0. So you have to again find x3. x3 is equal to x2 minus first derivative at x2 divided by second derivative at x2. That is 1.54. The slope there is minus 0.586. So some improvement is there. Earlier it was minus 3.73. Now it has become minus 0.586. So some improvement is there. So you have to again find x4, x5, x6, etc. until the tolerance of the slope is 0.001. So the slope should be less than 0.001. Then you can stop. Okay, so this is the end of single variable optimization algorithms. Okay, so next is the two variable optimization algorithms. Okay, that will be a little more difficult, so we can start that now. Okay, optimization of objective functions in two variables. So x and y will be there. So objective function will be f of xy. Okay. So first is the analytical method. That is how you find objective the minima of a objective function in two variables by calculus. So you have to find first derivatives and subject to conditions of optima checked by Hessian matrix or second derivative matrix. And this analytical method is only applicable to easily differentiable functions. Otherwise, you have to use the numerical methods, which you will learn later. The condition for minima of an objective function of two or more variables. So, if x star y star is a minima, then partial first derivatives must be equal to 0. That is, partial f by partial x, partial f by partial y at the x star y star should be equal to 0. So, in other words, it must be stationary point. Then, if x star y star is a minima, then second derivative matrix at x star y star must be positive definite or positive semi-definite. Okay. So, we already saw the definition of positive definite and positive semi-definite. Okay. So, this diagonal elements and leading principal determinants must be greater than or equal to 0, or eigenvalue should be greater than or equal to 0. And for maxima, Hessian matrix must be negative definite or negative semi-definite. So what is the meaning of negative definite and negative semi-definite. So it means that eigenvalue should be less than 0 or eigenvalue should be less than or equal to 0. So that is the condition for maximum. But usually people only study the conditions for minimum. Okay. Because maximizing problem, you can take negative and it will become minimizing one. So no need to study both condition for maximum and condition for minimum. Okay. So in the textbook, they only concentrate on the condition for minimum. Then condition for saddle point, the text are white. So the saddle point is a tabletop region. So it will look like this. The curve will come like this. And it will be flat for some distance and then it will rise again. Okay, so this is called tabletop region. Okay. So here first derivative is equal to 0 and second derivative is also equal to 0. So what is the conditions for the saddle point? So first derivative equal to 0, then Hessian matrix must be indefinite. So what is the meaning of indefinite matrix? Indefinite matrix means eigenvalue can be both positive and negative values. But in some, and also if at least two diagonal elements are of opposite signs, it is indefinite. But we can see that for other cases, it can also be indefinite. So what it means is that even if the diagonal elements are of the same sign, it can still be indefinite. So the reliable method is to check the eigenvalues. It should be both positive and negative values. Okay. So we can look at some examples of analytically how to find the minima of the objective function of two variables. So find the minima of this objective function. So what you have to do is that first find partial f by partial x equated to 0 and partial f by partial y and equated to 0. If you solve it, you get 2.5 and 1.5. X star equal to 2.5 and 1.5. Okay. So this is the stationary points where slope is 0. Then you have to check if the Hessian matrix is less, is a positive definite or positive semi-definite. So you write Hessian matrix or second derivative matrix at 2.5 minus 1.5. So if you take the eigenvalues, you get 1 is plus, 1 is minus. So this is definitely saddle point. Okay. Okay. No. Okay. So this is not eigenvalue. Okay. This is only the points. Okay. It's not eigenvalues. Eigenvalues are here. Okay. Eigenvalues are both positive. Okay. So this is minima only. Okay. The saddle point comes in the next example. Sorry. Okay. So check the optima of this objective function. So stationary point is already given. So there's no need to equate first derivative and find stationary point. It's already there. So you find the second derivative matrix of this objective function at 0, 0. So this is the matrix. So you can see that diagonal elements are both positive and you will think that it is not the saddle point. But if you take the eigenvalues, you find that one eigenvalue is 13 and another eigenvalue is minus 7. So it is of opposite signs. Hence it is a saddle point. Okay, then some numerical algorithms for two variable optimization. So this is very important. It will be asked for exam. Okay, all these algorithms. So all these numerical algorithms for two variable optimization assumes a convex function. Okay, so it assumes that So suppose this is xy, f of xy. So in this range, there is only a single cup. In the given range of x and y, there is only a single cup. Okay. And another important thing is that the formulation is only shown for two variables. That is, the equations are shown only for two variables. But you can simply add it to it and make it variable for x, y, z. That is 3 or 4 or 5 variables by adding on more similar terms to the equations. But with hand calculations, we can do only two variables. So direct search method or grid search method. So this is one popular numerical method. It is one of the simpler methods used for two variable objective functions. Okay, there is not much mathematics to it. It is only some sort of exhaustive search applied to two variable objective functions. So what you do is that you have to make a grid with the xy values. Okay, I think I already discussed this with you. Okay, from the range of x and the range of y, you divide the objective feasible region, xy feasible region, into a grid, and this value delta should be like 1/10 of the range of x or y. That is how we fix delta. Okay. Then the user has to start at a particular point. For example, this blue point. Okay, and he has to set the value of objective function at these 4 points. Okay. Okay. So this point is suppose this is xy. Okay. So this point is x plus delta x. This point is x minus delta x. So this is actually delta x. So grid size is delta x. This point is y plus delta y, or it is equal to delta. Okay. So delta y is equal to delta x equal to delta. And this is equal to y minus delta y. Okay, delta y equal to delta x equal to delta. That is the grid size. Okay, so you have to search this 4 corners. Okay, suppose the minimum value of objective function occurs here. Then what you do is that centered with this point, you search the 4 corners like this. Okay, so suppose minimum value is here. You come here. Then from here you search the 4 points like this. Okay, then you come here, and if you repeatedly do this, if there is only one minima in that objective function, you will definitely reach the minimum. Okay. Okay. So then search will convert to some local minima point. So one example is that find the minima of this convex objective function in the range of 0 to 4. So this is actually a spherical objective function with circular contours centered at 2, 3. Okay, there's x equal to y equal to 3 is the center of this objective function. Okay, so this is the answer which is shown in advance. Okay, so what you've done is that let us take delta as 0.2. So the range is 0 to 4. So delta should be 4/10 at least. It should be less than 4/10. So we are taking as 0.2. So let us make a XY grid. Starting point is 0, 0. So we'll start our search from 0, 0 here. So, okay, so this is the grid. This is our starting point. What you do is that from the starting point, you search these 4 points and you come here. Okay, then from here you search these 4 points and you come here. So I have plotted the progress of this search, okay, for up to some distance. So what is seen is that the grid search moves from 0, 0 to 1.2 vertically. Initially, it will go in a straight line up to 1.2, and after that, it is seen to diagonally move like this. Okay, it will move in this staircase fashion like this in a diagonal way, and eventually it will reach the 2, 3. Okay. So for convex objective function, the algorithm will eventually converge to minimum. Okay. And we have to stop the search when there is no improvement in the f of xy value from a grid point. Okay. Suppose your particular grid point is giving the best value and all the 4 surrounding values are giving higher values of the objective function. Then you can stop the grid search there. Okay, but actually, yeah, what is that?
I have one question, sir. Why it is till 1.2 it is going up? Why it is not
That
going
is
to the
the nature of this particular problem. Okay, when you plot this particular problem, it is going like this. Okay, maybe for another problem, it will go in a different way. Okay, huh?
Okay, sir.
Maybe it depends on grid size also.
Okay, sir. Okay.
Okay, so we have to stop the search when there's no improvement in the f of xy values from a grid point. Okay, suppose you reach a grid point, okay, your f of xy value is 10, and here it is 12, here it is 14, here it is 15, here it is 20. Okay, so then you can stop because you reach the minimum value and there's no improvement in the other 4 values. So, but another improvement is there in the grid search method where you can successively refine the grid. It is called Hook and Jeeves method. So what is done is that here we have become stuck. Okay, from this 10, all these objective functions are higher than 10. So you have to stop there. Okay, but you can still do some refined search by dividing this into another grid. Okay, and conducting a more refined search. So starting from here, maybe you can find a value 9 here, objective function value 9 here. Okay, so if you do further refinements like this, you can get better values. So in Hook and Jeeves method, first a coarse value of delta is used. Say delta equal to 0.2. Okay. Then if the search is stuck at some point, delta is refined to a smaller value. Delta is reduced to say delta by alpha. Say alpha equal to 2. So 0.2 is reduced to 0.2 by 2. That is 0.1. So the mesh in that final grid is subdivided into a finer mesh with a small grid size. Okay. Then delta can be successively reduced by a factor of 2 until no further improvement is obtained. Okay, that is you have to define a tolerance. Okay, define a tolerance. So if it is satisfied within that tolerance, we can stop the search. So next we look at Cauchy's method of steepest ascent. So we'll start this method and just look at the basics, and tomorrow's class we can look at the derivations. Okay, so this is a highly important method of optimization. Cauchy's method of steepest ascent. Steepest ascent will give maximization. Okay, steeper descent will give minimization. But we look at maximization because that is easy to visualize. Okay, now suppose we are climbing a mountain. Okay, climbing a mountain, we start at x0, y0 at the bottom. X0, y0 at the bottom. And suppose we want to reach the peak. This is the peak in the shortest route. So shortest route will be the steepest route. So this is the steepest route. Okay, and also because this is a symmetric objective function, the steepest route will take you to the peak. Okay, so for symmetric objective function, this is actually a cone. It is a symmetric objective function. That is symmetric about the vertical axis. So in the case of symmetrical objective functions, steepest route will take you to the peak. So you can see that if you take any other path, you will go to some height, h, and then you will come down. Okay, if you take another path like this, then you reach some height h1 and come down. So it is not worthwhile to take a non-steepest route. You have to always aim at the steepest route. So what is the steepest route? For steepest route, this angle theta must be maximum. Okay, so that the slope tan theta is the greatest. Okay, so this is the steepest route, and the projection of the steepest route on the xy plane, that is called del F. This is called gradient vector. Okay, so gradient vector is nothing but the projection of the steepest route on the xy plane. So how do you find gradient vector? So we can find gradient vector graphically. Okay, the method is that you okay, the direction of the steepest ascent at x0, y0 will be the normal to the tangent to the contour at x0, y0. So what you have to do, you have to draw the contour passing through x0, y0. Okay, so that is this circle. Okay, contour passing through x0, y0, and you have to draw the tangent to the contour, and this normal to the tangent will lie under this steepest route. Okay, so basically you draw the contour at x0, y0, you draw the tangent to the contour at x0, y0, which is your starting point, and you draw the normal to that tangent, so that will give del F. That's the gradient vector. Okay, and alpha is only the angle made by del F with the x-axis. Okay, so this is the graphical method. Okay, but in practice, nobody will do this graphical method. So mathematical method is there. So we'll see the equation.
Sir, alpha and theta are the same here, right?
No. Theta is the elevation. That is the steepest route at a certain angle theta above the gradient vector. Alpha is the angle made by gradient vector with x-axis. Okay.
X-axis.
So yeah, this is the xy plane. Okay.
So does it mean it's 3D angle versus 2D angle? Theta is in 3D angle, whereas alpha is 2D angle.
Theta is the height of the altitude. Okay. It's the angle of the steepest route which is above the gradient vector. Okay.
So basically, sir, alpha is when the steepest route is projected on xy plane, then what is the angle is making with x-axis, right, sir?
Yeah.
Projected length of the steepest route on the xy plane and angle with the x-axis. That is the alpha, right, sir?
Yes. Okay.
Thank you, sir. Thank you, sir.
Okay, so this is the graphical method which nobody use in practice. This is del F, this is the y-axis, this is the x-axis. So in mathematical notation, y is called j and x is called I. So you can find this distance, okay, delta y. This delta y or b is found to be equal to partial f by partial y at x0, y0. Okay? And the delta x or a is found to be equal to partial f by partial x at x0, y0. Okay, so this is the del F projection on the xy plane. So this distance is a, this distance is b, and the value of this b is this thing, and the value of a is this thing. Okay. So this is alpha. So from this you can write the equation of the del F is there. Del F is equal to alpha I ai plus bj, where a is this a partial derivative with respect to x at x naught y naught. B is equal to partial derivative with respect to y at x naught y naught. So you can find vector of del f easily without drawing any contours or anything like that. Then tan alpha is b by a. Then, okay, then a highly important thing is there. So this is for steepest ascent. Okay. So then for steepest ascent, so for minimization, you have to have steepest descent. So you have to climb down. Okay, so okay, so this is steepest ascent. Okay, so del f will look like this. Okay, del f, so del f will look like this, and to minimization, it is steepest descent. So del f will be in the opposite direction. Okay, so it will be so this is plus del f, this is minus del f. So minimization is in the direction of minus del f. Okay, so minimization, you have to take minus del f. So you have to find minus of partial f by partial x and minus of partial f by partial y. Okay. And how to find this elevation angle theta? It can be shown that elevation angle theta is equal to absolute value of del f vector. Okay. Okay, that is root of partial f by partial x whole squared plus partial f by partial y whole squared at x naught y naught. Okay. But this is not important. Okay. Okay, then another highly important thing at which we'll stop this lecture is that if you have a unsymmetric objective function like this, okay, so this is unsymmetric about this z axis. Okay, so suppose we are starting at x naught y naught and we find the steepest ascent direction. So you can find that steepest ascent direction will take you here, but peak is here. Okay, so what you have to do is that after you reach here, you have to change direction again. Okay, so it is found that if the objective function is unsymmetric, you cannot reach the peak in one step. Okay, multiple changes of direction is required. So this figure represents the successive changes in direction to reach the peak for a unsymmetric objective function. So you have to do zigzagging at right angles like this at various contours. So we can stop here, and how we do this, we look in the next class. Okay.